Good morning, everyone. We'll continue our lectures today. Here we have a question about Coulomb's law. The question says two protons inside a helium nucleus have a typical separation of a 3 femtometer. What is the force between these two particles? If no other forces are acting, what is the acceleration experienced by one of these protons? The mass of proton is 1.67 10 to the power minus 27 kilograms. And we also have here E equals to 1.602 10 to the power minus 19 Coulomb. So at the beginning, let's talk a bit about this E. E is the smallest charge unit that is designated for elementary charge. So in this case, if I am to look at the relationship between the charge and the current, I know that the current is dq over dt. And in this case, I can say that if I am to integrate, then this charge equals to the current times the total time. So in standard units, the charge Q here is Coulomb. So what does Coulomb mean? 1 Coulomb is the total charges that gets accumulated due to a current of 1 ampere for 1 second. And experimentally, they have found that this 1 Coulomb is indeed 6.242 10 to the power 18 charge of protons. What does this mean? If I am now to find the relationship between this E, which is my elementary charge, that is the smallest charge unit, as I said, then 1E equals to the inverse of 6.242 10 to the power 18, and then 1E is 1.602 10 to the power minus 19 Coulomb. So this is my charge, the equivalency between the elementary charge and the Coulomb. So whenever we see the elementary charge, we can say that what is multiplied by the elementary charge is basically the number of the protons if it's positive, or the number of electrons if it's negative, as we will see later on. In one of the examples where we have the sodium with 2 plus 2, this means that the charge on this ion is due to 2 protons. I can write it as 2e, and then I can say that the total charge for this ion that is positive is 2 times 1.602 10 to the power minus 19 Coulomb. If it's an electron, then the charge would be minus E. Okay, so this is the E. Let's go back to our question. And our question, we said that we have 2 protons, which means those 2 protons, one of them is, let me call this one Q1 is 1E, and the second one is Q2 is also 1E, while the distance between them is 3 10 to the power minus 15 femtometer. If I am to calculate now the force, then as you know, those are from the same type, same signs, which means that the forces will be repulsive. So let me call this one F1, and let me call the other one as F2. So this is green color will induce F2. Don't forget that magnitude-wise, those two forces are equal. F1 equals to F2. Why? Because they both are due to the contribution of both charges. So I have here K, Q1 magnitude, Q2 magnitude divided by R squared. And in this case, I have F1 equals to F2 equals to 8.99, 10 to the power 9 times, I can say 1.602 minus 19 squared divided by 3, 10 to the power minus 15, also squared. And in this case, I have F1 equals to F2 equals to 25.7 Newton. Now, the second part of the question is asking for the acceleration experienced by one of these protons while the mass, so if this is A, then this is B. He gave me the mass of the protons, 1.67, 10 to the power minus 27 kilograms. Then I know that F equals to mass times the acceleration. Then magnitude wise, A equals to F divided by M, or A equals to 25.7 divided by 1.67, 10 to the power minus 27. And in this case, the acceleration is 1.54, 10 to the power 28 meter per second squared. Now, let's move to how is this force is being exerted by one charge on another. If we can call that this force is an action at a distance. Why? Because we have seen that two particles that are far apart are exerting forces on each other, so they do have an influence. Now, how is this influence happening? For example, if I have this charge B that is a negative charge, and I have this charge that is a positive charge, so this is a negative charge, this is a positive charge. Based on Coulomb's law, I can calculate the force exerted by A on B, and I can see that this force is an attractive force because they are from opposite sign and they are directed toward the positive A this way. Now, what's going to happen if this charge moves a bit? Is this force going to change as well? Is this force going to move as well? The answer to this question is yes, because if I am at position 1, then this force would be the force exerted due to A on B. If my charge moves to position 2, then definitely based on Coulomb's law, I have a different force that have, if the distance has changed, then I have a different magnitude, and also I have a different direction. So as you can see that the direction is always pointing, because it's an attractive force, it is pointing toward the charge the charge A. The first thing we need to understand is this force is changing instantaneously, since Coulomb's law does not have any time dependency in its function. So that force changes instantaneously, which means that the field that causing also that force to change is also changing instantaneously. So how does it work? This field as a vector field at any point surrounding this charge. It has a magnitude and a direction. If we want to understand it, we need to compare it with the gravitational field. Gravitational field, for example, due to the Earth, we can see that this gravitational field is a vector field. However, closer to the surface of the Earth at a small area where it looks flat, I can say that this gravitational field is uniform, which means it has the same magnitude anywhere and the same direction pointing toward the Earth. So this gravitational field G has a value of 9.8 meter per second squared. If you multiply by the mass, you can get the gravitational force. So if we look at the Earth from far distance, I can see that this gravitational field is always pointing toward the Earth. However, the magnitude is different based on how far is this mass object from the Earth. As we will see later on, this is no difference than the electric field. So if we assume that this is my charge, and here my charge is a negative charge, and as you can see, we're treating it as a point charge. The electric field is always pointing toward the negative charge. And again, the magnitude depends on the location of that point from the charge. However, if I have a positive charge, in this case, the electric field will be pointing away from that charge, and the magnitude will depend on how far is this location from my charge. I'll call this one R. So in order to understand how is this electric field formulated, let's look at this example. Here in this example, we have a sodium atom with one E and a calcium ion with two E. So both of them are positive, that are at a distance of R. So what is the force exerted between those two ions? Based on Coulomb's law, I can write that this F equals to K, the first charge is 1e, second charge is 2e, then divided by r squared, and this force is pointing away because it's a repulsive force, and that's why the unit vector here is I hat. Now, if I do the same by changing the charge that I am exerting my force on from calcium to E to lithium 1E, then the electric force exerted due to the sodium on the lithium is this. Again, Ke over r squared, and it's pointing in the positive direction of x. That's why it is I hat. However, if I put a fluorine here with a minus 1e, then the force would be attractive and will be pointing in the negative direction of the x. Now, if I compare now those are three relationships that has this sodium as fixed, while the other charges that I am exerting forces on have been replaced or changed from calcium to lithium to fluorine, and try to find what is the common in that equation between those three equations. I can say that if I take the K times the charge of the sodium divided by R squared times the I hat, I can say that this is the contribution of my sodium ion. And in this case, I will call this as the electric field due to the sodium. So here in this case, I will write E equals to K plus E divided by R squared I hat. Same thing here. K plus E divided by R squared I hat. K plus E divided R squared also I hat. Now remember that this negative that came from the second charge. So this is the common relationship between those three. Then what I can conclude? I can conclude that the electric field that is generated by this sodium charge is K times this charge that is generating the electric field divided by the distance squared, or the square of distance, which is the distance between my charge and the point of interest, and I hat defines the direction of my electric field. What does this mean? This means that this charge that I had as sodium plus 2 at this location is generating an electric field pointing away. So this is for the case of the sodium, was pointing away in the positive x direction. In general, it is r hat. It depends on your location that you're interested in with respect to the location of the charge that is generating the electric field. What else? I can also conclude that if I multiply the charge that does exist in the electric field of the first one with the electric field at this location, I will get the force. We're going to look into this more in details in the coming slides. So to repeat what we have just said, a positive charge will generate an electric field such that it is pointing away in all directions. A negative charge will generate an electric field such that it is pointing toward this charge in all directions. Okay, so let's look at this example. We said that a negative charge will generate an electric field that's pointing toward the negative charge. That's fine. So if I have this electron that is minus E, and I am interested to calculate the electric field in this location, let me assume that this is called P, then I can calculate the magnitude E equals to K Q divided by R squared. Here I have the distance as 1.9 10 to the power minus 8 meter. K is 8.99 to the power 9. And the charge magnitude is 1.6 to the power minus 19. So what is the magnitude? The magnitude is 4 10 to the power 6. However, since the electric field is pointing toward the negative charge, then it will be in the negative direction of the x-axis, and that's why I wrote it as E equals to 10 to the power 6 minus I hat Newton per Coulomb. So what did I understand from here? I understood that the electric field for the case of the negative charge is always pointing toward the negative charge, and the expression for calculating the magnitude of the electric field is given by kq over r squared, which means it is proportional to the charge, inverse proportional to the square of the distance. So in this case, if this is E, if I am to calculate the electric field right at this point, then here the distance is different, r2, that is less than r. And in this case, because the distance now is smaller, is less than the first one, then I can say that the magnitude of the electric field here is greater. So if I am to call this one E2, then E2 magnitude is greater than this E. Why? Because now the distance here, because R2 is less than R. Now, what happens if I bring a proton, a positive charge, and I put it in this location, the one that I used to call P here? Then, if I apply this expression that I've seen earlier, which is F equals to QE as a vector, then if my charge that I'm multiplying by this vector E is positive, then definitely the force would be in the same direction of the electric field. So if I substitute the electric field that I got earlier, which is 4 times 10 to the power 6 minus I hat times this charge, which is a positive charge, 1.6 to the power minus 19, then I can get the force to be in the same direction as the electric field. So what did we observe here? We observed that if the charge that I am evaluating the force at is positive, then the field at this point would have the same direction as that force, or the force at that point will be in the same direction as the direction of the field. Now let's look at a positive charge. For the case of the positive charge, I know that the electric field will be pointing away. In this case, if this is my location P that I talked about, I'm interested to find the electric field right at the point P that is R away from the charge, then the electric field will be pointing also away. Now, since this line is along the x-axis, then in this case, I can calculate the magnitude of the electric field as kq over r squared. Q here is a sodium, so this is sorry, a calcium. So in this case, I have the magnitude of the electric field, KQ over R squared, and then the magnitude would be 2 to the power 6. So this is the magnitude of the electric field. Now, what is the vector? Since this electric field is pointing in the positive direction of the x-axis, then it will be I hat. Again, this is calcium. If I am to calculate now the force exerted on an electron that I put here at the location P, then if I apply this expression F equals to QE, if this charge is negative, then this Q will be negative, and that's why it is minus 1.6 to the power minus 19 Coulomb. Here in this equation, I substituted Q with its value of a negative value, well, minus 1.6. Why? Because I'm expecting the force to be in the opposite direction of the electric field because of this negative sign. So in this case, the force would be in the opposite direction of the electric field, and that's why it is minus I hat. Okay, so what we can understand from this example, two things. The first thing is the induced electric field at any point, if the charge that is inducing this electric field is positive, will be pointing away. If I put a charge in this location that I calculated the electric field, and this charge was positive, then the force would be in the same direction of the electric field. If this charge that I put at the location where I calculated the electric field is negative, then the exerted force will be in the opposite direction of the electric field. So this is extremely important. One thing you need to pay attention to and be careful with is the electric field is induced due to at least one point charge. Which means if you have one pointed charge, definitely you have electric field in the surrounding area of this charge. Which means electric field will not be zero. However, the force anywhere surrounding that charge will be zero, of course, because the force requires at least two charges. Look at the equation, look at the expression for the electric field and the expression for the electric force. Electric field, you only need one charge to generate an electric field in the surrounding. You definitely need two charges at least to have an electric force. So the electric force will be exerted due to the existence of at least two forces. And also, if the charge that you are evaluating the force on, where you calculated the electric field, is negative, then you can see that the direction of the force is in the opposite direction of the electric field. If the charge that you are evaluating, so this is the point P we talked about. If the charge that if you are evaluating the force on at the same location where you calculated the electric field is positive, then the electric field is in the same direction as the force. Superpositions is also exist in the electric field. As we've seen before on the electric force, there are vectors. So if you have several charges and you're interested to calculate the total charge at one specific point, then you need to calculate the electric field for every due to every uh, point charge, and then do a vector summation, add those vectors together. For example, if you need to calculate the total electric field at this point and the total electric field at that point, you will see that you need to calculate the electric field due to Q1 and the electric field due to Q2 at this point, which is, as you can see, this is a positive charge. That's why E1 is pointing away. This is a negative charge. That's why E2 is pointing toward the negative charge. And then by adding those two vectors together, you can calculate the total electric field. And you know how to do that. You need to take the calculate the components on the x and on the y's, and then reconstruct the total force. And exactly the same here, x and y, and then project the component on the x and y, find the components for the total electric field, and then reconstruct it again. Be careful when you calculate the vector for the force or for the field. Always remember when you do calculate the components for those vectors, you need to project the calculated magnitude on the x and on the y, which basically after you calculate the total magnitude of the f, then you project it on the x. You don't project the distance between the point of interest and the charge. So you don't project this distance. You project the magnitude of the force, and then this way you can calculate the component. So be careful for this, because it's going to give you a wrong answer if you project the distance assuming that this is the fx, which is wrong. You calculate the total the magnitude, and then you project this magnitude. Okay, so for this example, we have a negative charge Q1, that is minus 1.21 microcoulomb. We have a positive charge, 3.4 microcoulomb. We need to calculate the total electric field at the point D, given the coordinates x and y's, as you can see here. So how do we do this? Again, we will be using the superposition technique. We have the first charge here, second charge here. Let me do this one in red. Or this one is a Q2. That is 3.4 and the other one is Q1 minus 1.21 minus 6, and we need the location here. D, while my coordinates are X and Y this way. So how do we calculate the electric field? The first thing is we draw the lines between, those are my R's, this distance. So this distance, let me call R2, as 6.83 power minus 6 meter. And this distance, R1, is 3.19. So this is Coulomb meter. For Q1, since it's a negative charge, then the vector would be pointing toward this negative charge. So I have my vector here as E1. Also, this angle is 30 degrees. I have my E2 due to Q2, since it's a positive charge, pointing away. So this one is E2. Then my total electric field is the summation of those two vectors, and it's indeed expected to be this one is E2. But how do we calculate it? First of all, we calculate E1. So E1 equals to K Q1 magnitude divided by R1 squared. And in this case, E1 is 8.99 10 to the power 9 times 1.21 10 to the power minus 6 divided by R1 is 3.19 10 to the power minus 6 squared, and then E1 is 1.07 10 to the power 15 Newton per Coulomb. And then for E2, again, 8.99 10 to the power 9 times 3.4 10 to the power minus 6 divided by the distance is 6.8 3 10 to the power minus 6 squared, and then I have E2 equals to 6.56 10 to the power 14 Newton per Coulomb. So this is the magnitude of the electric field for E1 and E2. And in this case, I need now to calculate the total electric field. I will calculate the components of this total electric field. I'll extend this. So I have this as 30, and also so this is the x and this is my y. So in this case I have the x's. So E2 will be projected on the x-axis. It is E2x, and also projected on the y. It will be E2y. So the angle here is 30, and this also is 30 degrees. So if I am to look at E dot x, it will be E1, and now because E2x is in the negative direction, it will be minus E2x. Now E dot y, I only have one component, which is a negative component, which is minus E2y. So both the x and the y's are negative. So how much E dot x? E dot x is E1, which is 1.07 10 to the power 15 minus E2x is E2 cosine 30, and E2 is 6.56 10 to the power 14 times cosine 30 degrees. Then E dot x is 5.02 10 to the power 14 Newton per Coulomb. It's a positive value, which means it is pointing in the x direction. So E1 is greater than E2x, and then I have E dot y, that is minus 6.56 10 to the power 14 times sine 30 degrees. And in this case, so this is my E dot x. In this case, E total y equals to minus 3.28 10 to the power 14 Newton per Coulomb. Now, if I want to calculate, as you know, the vector, I need to calculate the angle as well. So in this case, I'm looking for this angle. And this angle is the E dot x. This is E to y, and which is also the E dot y. So this equals to E dot y, because it's the only component that is contributing, which is tan inverse of E dot y over E dot x, and theta equals to minus 33 degrees. Why? Because this one now is e tot x, and this one is e tot y. So it would be e tot y, tan inverse of e tot y over e tot x. So minus 33 degrees, which means 33 degrees below the x-axis. Now the detailed solution is also here for you. Now you can try this on your own. This is exactly what we have done earlier. I want you to try this one on your own. The answers to A and B is here. The first question A is asking you, after you find the electric field here, if you put a point charge, positive point charge of zero point 0.5 microcoulomb, how much would be the electric field, the electric force? And in the second B, if this charge is a negative charge of minus 1 microcoulomb, how much would be the electric force exerted on this charge? So put the charges here and calculate the electric force on that charge.